Hello and welcome. In this video, we're going to be talking about the fundamental concepts of Coulomb's law, effective nuclear charge, and electron shielding as they pertain to periodic trends like atomic radius, ionization energy, electronegativity, etc. The reason why we need to first start out with these three fundamental concepts is that if you're going to understand how the periodic trends work, you first have to understand the foundational concepts that determine those periodic trends. So let's go on and jump directly on into this. Okay? So Coulomb's law is the first place that we need to stop and talk about periodic trends, okay, and what governs those trends. And when we look at this equation, that force equals K times Q1, Q2, all divided by R squared. This is what gives us a fundamental idea of the forces of attraction that are occurring between the nucleus and the electrons within an atom. We can also use this same equation to talk about repulsive forces. Okay? So when we look at the equation, F is our electrostatic force, typically of attraction. K is what's called a proportionality constant, or Coulomb's constant in this case, which has a value of 9.0 times 10 to the ninth Newton meter squared per Coulomb squared. Not that you have to memorize that. Then Q1 and Q2 are your charges, or the amount of charge. And if we're talking about attractive forces, then Q1 is typically going to be your number of protons. Q2 is going to be your number of electrons. And then R squared, that is the radius between the centers of charge. And we measure this from the center of a nucleus to the center of another nucleus if we're talking about attractive forces or repulsive forces between atoms, or we can measure it from the center of the nucleus to where the electron is going to be. And if we're talking about attractive forces within an atom, which is what we talk about when we're dealing with periodic trends, then that distance, or R squared, is going to be measured from nucleus to the electron. If we're talking about a repulsive force or atoms, then it's nucleus to nucleus. So in this Coulomb's law, one of the things that many students don't recognize is that this is what we refer to as an equality. We've got an equal sign in there. And then that value of K, that proportionality constant, is what allows it to be the equality. It's what makes the entire equation work. Well, you can derive proportionalities by removing that proportionality constant. So if force equals K times Q1, Q2 divided by R squared, and we remove that proportionality constant, we get two relationships. First one is that force is proportional to Q1 times Q2. And the second proportionality is that force is proportional to 1 over R squared. So what exactly does this mean? Why is it important? Well, let's take it proportionality by proportionality. So the first one, force is proportional to Q1 times Q2. In other words, force is proportional to the amount of charge that you have. So if you increase Q1 or Q2, or increase both of them, you're going to see an increase in that attractive force or repulsive force if they have the same charge. Likewise, if I decrease the amount of charge, decrease Q1 or Q2 or both of them, I'm going to get an overall decrease in the amount of force that I have. So that is the first proportionality. The second proportionality is this one that force is proportional to 1 over R squared. In other words, force is inversely proportional to radius squared. So what this means is that if I increase the radius, I'm going to end up decreasing the force. Likewise, if I decrease the radius, I'm going to increase that force. But what's key in this is that it's not just a one-to-one relationship, but rather I've got that square in there. And that makes a huge difference. Because what this means is that if I double the radius, I don't just half the force. Or if I half the radius, I don't just double that force. It's a squared factor. So let's look at some examples of this and show how these proportionalities work. So based on Coulomb's equation, what do you think is going to be the effect on force if we do these four things? If we have both charges being doubled, or if our radius is halved, radius is doubled, or both of the charges and their radius are doubled. So to answer these questions, we're going to be looking back at these proportionalities. So the easiest thing to do is to go on and assume that everything equals 1. So initially, the idea would be that I have a Q of +1, a Q2 of -1, and I'm leaving off the positives and negatives right now, which means I would start out with a force that's proportional, in essence, to 1 or 1 times K if we plug it back into the equality. So if I double both of these charges, Q1 becomes 2, Q2 becomes 2, and now I get a force that's proportional to 4 times what it had been. And again, if we plug this into the equality, force would equal K times 4, right? Assuming radius stays constant. So doubling both charges, the doubling of one charge causes a doubling of the force, a doubling of the other charge causes another doubling. So altogether, if I double both charges, my force increases by a factor of 4. So that's how we'd use that first proportionality. So what if radius now is halved? Okay, well, again, let's start out and assume a radius of 1. So 1 squared would equal 1. So force would be proportional to 1 over 1, or simply 1 times K when we plug it back into the equality, assuming that our charges stay constant. So what if I half this? Well, that means that my radius is now going to go to 0.5. And 0.5 squared is 1/4, or 0.25. So now what I have is that force is proportional to 1 over 1/4. And when I'm dividing by a fraction, I can multiply by the reciprocal. And what this means is that I get force is proportional to 4 times what it had been. So again, that squaring effect has huge implications. So when I half that radius, I actually see that force go up by a factor of 4. So now then, what if the radius is doubled? Well, we can go back to the initial idea that radius was 1 and get that force would be proportional to 1. And if I double that radius, so now I have 2. So 2 squared is 4. So force would be proportional to 1 over 4, which means I see my force as now just a fourth of what it had been. Okay? So again, that squaring has huge implications. And then lastly, what if both charges and radius were doubled? Well, this is where we have to combine these two proportionalities and get that force would be proportional to Q1 times Q2 all over R squared. And again, if I start out assuming that everything has a value of 1, then force would be proportional to K times 1 when we plug it back into the equality. But now then, I'm going to double both charges. So that goes to a charge of 2, a charge of 2. Radius gets doubled. So that's now 2 squared. So I have 4 and 4, which means force would be proportional to 4 over 4, or in other words, 1. So if I double both the charges and I double the radius, I actually find that force doesn't change at all. Now, again, why is this important? Well, when we get into periodic trends like atomic radius, ionization energy, electron affinity, etc., radius has a huge effect on what happens with those trends. Okay? Affected not just by increasing the number of protons and the number of electrons within an atom, but then what happens to radius when we start adding in those electrons to that atom, and how that radius is going to have a larger effect on force typically than what the increase in charge does. But at the same time, sometimes the increase in charge and that increase in radius can offset each other. So that is Coulomb's law, which brings up now the idea of effective nuclear charge. So Coulomb's law allows us to measure or calculate what that attractive force is. The way that we then talk about that attractive force in general terms is through effective nuclear charge. And this is symbolized as Z sub EFF, often referred to as ZEF, and it's the net positive charge experienced by a single outer shell electron of an atom. Easier way to think about this is it's simply the pull that the electron feels due to that nucleus, that positive charge, because positive and negatives are going to attract each other. And how strong that attraction is, as measured by Coulomb's law mathematically, is then represented as effective nuclear charge, or ZEF. So to give you kind of an idea of how this looks within an atom, when we're looking at this, and I know the definition says outermost electron, but we can actually talk about the ZEF of any electron within that atom. So in this particular depiction, I've got an electron of interest. There are outermost electrons, but note that those outer electrons have no effect on the effective nuclear charge between the nucleus and the electron of interest. So this attractive force between this electron of interest and the nucleus, that would be the ZEF. Okay? And what we'd find if we calculate this using Coulomb's law is that because the radius between this electron and the nucleus is smaller than the radius between, say, an electron out here and the nucleus, this would have a stronger ZEF. In other words, it's pulled closer into that nucleus. There's a stronger attraction, and therefore it's more difficult, or it requires more energy to remove that electron as compared to one that is further out. So we get this idea that the further out the electron is from the nucleus, the easier it is to remove it. And again, this has big implications when we start talking about things like ionization energy, electronegativity, etc. So that is effective nuclear charge. Now, other thing I want you to notice in this, electrons in between cancel some of that nuclear charge. And that canceling out of effective nuclear charge, that's what we call electron shielding. And this simply refers to the inner energy level electrons helping to reduce, or in other words, shield those outermost electrons from the full pull of that nucleus. So the way that I talk about this in my classes is, imagine you're at a dance and the person that you're interested in dancing with is across the room from you. And you're trying to get their attention, but you've got the entire dance floor in between you and them. Well, that dance floor is shielding you from being able to get their attention. So in other words, your attraction to them or their attraction to you is decreased because of not just distance, like we see in Coulomb's law, but because there's other things in between you and the object of interest that's shielding from that attractive force. So when we look at this in this form, here's what I want you to notice. We've got our nucleus, that would be our positive charge. We have inner electrons, and because they're the ones closest to the nucleus, they do not experience any type of shielding. There's nothing between them and the nucleus. So there's nothing to diminish that effective nuclear charge that we would see between the inner electrons and the nucleus. But these outer electrons, they're being attracted inwards. They have a certain ZEF, and again, the mathematical or the numerical value of that ZEF we could calculate using Coulomb's law. But the thing is, as these outermost electrons are pulled inwards, they have to deal with these inner electrons. And because these electrons are all negatively charged and like charges repel, as those outer electrons are trying to be pulled inwards by that nucleus, those inner electrons push it right back out. So the way I describe this is, you finally make your way across that dance floor and you're ready to ask that individual to dance, but then their group of friends surrounds them. You got to go through them. And that's what's happening in this atom. those inner electrons are blocking the nucleus from being able to attract those outer electrons more strongly. So in essence, they reduce the effective nuclear charge. The other key thing with this is that the more electrons an atom has, the greater distance away from the nucleus those electrons are going to be. Because if I add another layer of electrons out here, where I'm pointing my cursor, now not only does the nucleus have a further distance in which to have an attractive force, which again, going back to Coulomb's law, as radius increases, force of attraction is naturally going to decrease. Well, not only do we have that effective nuclear charge decreasing based on Coulomb's law, but as these outer electrons are now trying to be pulled inwards, not only does it have the group of friends, but it's got the entire dance floor still blocking them. So as a result, those electrons are able to move even further away from the nucleus than what they would naturally, because there's not enough or as much of an attractive force pulling them back inwards. So, in summary, Coulomb's law, this shows the mathematical relationship between force of attraction, charge, and the radius of an atom. Effective nuclear charge, this is the measure of pull an electron feels towards that nucleus. And then electron shielding, this is the measure of the reduction in pull an electron feels towards that nucleus. So hopefully all this has made sense. If not, feel free to leave me questions in the comments section and I'll get back to you as soon as possible. Also, if you have questions or ideas for future videos, leave those in the comments as well. Thanks and take care.